Let's take a look at question 131 from the closure, including part C. If we want to create a model for a set of data, find the least square regression line, we're doing it in Desmos this year. Everything that we do here, we can do in a TI-84 plus calculator, and that's normally what we've done in the past. But this year, we're using Desmos almost exclusively. So I begin by inserting a table. It's the plus, insert a table. And now I'm just going to go ahead and type my data. One of the things that you could consider after you enter the list in Desmos is, did I enter the values correctly? One of the ways you can kind of check that is to use something called checksums, and you'll see that our textbook lists that a lot. But basically it tells me that, hey, if I entered all this data and I added them up, I should get the same value that the checksum says. So if you look in this problem, it said the x value should add up to 718 and the y value should add up to 1202. So this is just a good technique to kind of help eliminate the possibility that there was some data entry errors. It doesn't guarantee it, because you could make a couple different errors that cancel each other out, but at least you're making an attempt to see if the data was entered correctly. So what we would do is just type the word total, T-O-T-A-L, and then in parentheses just type the list that you want the total of. When I do that, you can see that, yeah, my x values added up to 718, and I can just change this to y1 because I don't actually need this value anywhere else, so I'll just y1, and my y values add up to 1,202. So I'm sure that my data was entered correctly. If I want to go out and see these data points, I can see my smallest. Let's see, I need to bring this down a bit. There they are. There's the data. So now I have a decent view of my data set, and I can see that, yeah, definitely it's increasing. I would say, just based on looking at this, a linear model wouldn't be inappropriate. So to come up with the line of best fit, we're just typing y1 and then the tilde and then mx1 and then plus b. So when I do that, I get my line of best fit is y equals about 1.5 times x plus the number 8. So I would write it like that, y equals 1.5-ish x plus 8, or y equals 3/2 x plus 8. I can look at the residual plot, and when I look at it, I feel pretty confident that, yeah, it does go high, low, high, but then there's some randomness in here. So I'm not, based on these couple extra points over here, I'm not thinking that we would reject a linear model. I think a linear model is probably a pretty good fit. Problem part C asks us to, part C says, compute the correlation coefficient and interpret an R squared in context. So we do see here R, the correlation coefficient, and it is 0.955 or 0.96. It's very strong correlation coefficient. The other thing we see here is R squared, and I've called this the coefficient of determination, I think, but it literally is just this number times itself. So if you were to put 0.9558 in your calculator and square it, this is the value that you would get. And R itself doesn't have any real context to this particular problem. It's just a kind of a strength of a linear association, but R squared does have a meaning in context. And we write it down as R squared, or sometimes our textbook, I think, uses capital R squared, but it has this meaning, and it goes like this. Roughly 91% of the variation in the number of cups of ice cream sold can be explained by a linear relationship with temperature. So this seems to indicate that a lot of what we see going on in terms of how many cups of ice cream we sell is influenced by the temperature. In fact, 91% of the variability in the number of cups of ice cream can be explained by a linear relationship with temperature. So that means that there's 8% that could be explained by other things, like is it the day of the week, like on a Monday, maybe it's the time of the day also, but but temperature is a big influencer. And that's all I have to say about that.